Hey, flipped chemists, how you doing? We are diving into the next lecture, which is about solids and liquids. Get it? Diving into liquids. Ha! I know. I've got them all of the time. We are leaving gases behind us and moving into other forms of matter. So, as we do that, we want to talk about the intermolecular forces between molecules of a substance. The main difference between gases and liquids and solids is how much the molecules of that material like each other, how much they're attracted to each other. The more they are attracted to each other, the more dense they will tend to be. And so intermolecular forces are the things that make a liquid or a solid not a gas. And the broad category here is just called intermolecular forces. We're going to look at three kinds of intermolecular forces. The most common of them is called a dipole-dipole interaction, and this is a polar molecule. So you remember polar molecules have partially positive and partially negative parts of the molecule. So the partially positive parts of one molecule will be attracted to the partially negative parts of another molecule, and those molecules will hang out closer to each other than if they didn't have that attraction. The strongest of these dipole-dipole interactions is called a hydrogen bond, and that's when oxygen is bound to hydrogen and then bound to something else. And so oxygen-hydrogen is a very polar bond, and because oxygen can have two bonds, only one of them goes to the hydrogen, the other bond on the oxygen goes to some other molecule, and so it drags that molecule along as this very polar bond is out here grabbing a hold of other very polar parts of molecules and making them all sit close together. So hydrogen bonding is the most common part or type of dipole-dipole interactions. Here's just a picture of dipole interactions. Partially positive part of this molecule attracted to the partially negative part of this molecule and repelled by the partially positive part of this one. So they orient themselves so the positives are near the negatives and the negatives are near the positives, right? Law of charges stuff. This is another example here. We have a very polar molecule, which is it's like methane, but three of the positions have been replaced with chlorine. So it's very strong dipole going in this direction. They will all orient themselves so that the hydrogens are facing the chlorines, and they will line up with these dipole-dipole interactions. Okay, hydrogen bonding, the strongest of the dipole interactions. The hydrogen is positive, or partially positive, and the oxygens are partially negative. So hydrogens will point towards oxygens, oxygens will point towards hydrogens, and they will all sit very close together. Okay. Dispersion forces are the weakest form of intermolecular attractions. It's when it's not polar. It's just that because of random electron migrations around an atom or around a molecule, some part of a molecule just randomly happens to get positively or negatively charged because the electrons at that instant are not evenly spread out around the molecule. So it's an instantaneous temporary dipole, and these temporary dipoles can attract each other, and this is why nonpolar molecules aren't always gases, because these London dispersion forces are strong enough to hold it together a little bit. But nonpolar molecules tend to have much lower boiling points and much lower melting points, because it doesn't take much kinetic energy to knock them loose from each other and send them flying out into space, right? Much, much lower intermolecular force than a real dipole. Larger molecules are more apt to exhibit London dispersion forces, which is why, as we get into organic chemistry later, you'll see that the longer the chain of carbon molecules, the higher the boiling point. And that's going to be true as a general trend, because the bigger the molecule, the more they can find these London dispersion forces to attract each other. Okay, not why nonpolars have a lower melting and boiling point than polar molecules. So, just some pictures of this. If a neon atom were to happen for a moment to have electrons orbiting over here and no electrons in this region, then we'd have a partially negative and a partially positive, and that could induce a similar charge in another neon molecule and make them want to stick to each other. Okay, but that'll only last until these electrons orbit back around the other side. So again, uneven distribution on one atom can induce the uneven distribution on another and make them attract each other. But that just is temporary, instantaneous stuff. Okay, now a solid. A solid is a material which at a given temperature has a strong enough intermolecular attraction so that its molecules stay in contact despite the vibration caused by its thermal energy. So thermal energy is always wanting to drive the molecules apart. Intermolecular forces are wanting to drive the molecules close together. If intermolecular forces win, then you have a solid or maybe a liquid. If kinetic energy wins, then you have a liquid or maybe a gas, depending on how big the victory is, right? Solids generally don't diffuse. They can a little bit, but if you put a block of granite in the middle of your room, you're going to be waiting a long time for that granite to disperse itself into the air, right? Great-grandchildren will come see the same block of granite. So diffusion, dispersion happens very, 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 very slightly in a solid, okay? They're non-permeable. You set a solid on top of something else and it doesn't go through it. It just sits there. And solids have a defined shape and volume. They don't change their shape or volume with forces from the environment, okay? Different from a liquid, and so we'll see that in a minute. Heat and as heat goes up, the vibrations get stronger, but the intermolecular forces are able to still keep a solid as a solid. Crystalline versus amorphous solids. Crystalline solids arrange themselves in regular geometric patterns. Amorphous solids do not. Amorphous solids just kind of glob together. Crystals, there are lots of kinds of crystals. I'm not going to list them all here because your hand doesn't want to fall off as you write, but there are lots of kinds of crystals. The main idea to remember about a crystal is it's a regularly repeating geometric pattern. Amorphous solids are not. There is also something called a supercooled fluid, where the molecules are still in motion, but they're in motion very, very slowly, and so we call it a supercooled fluid, okay? Here's some examples of crystals. Crystals come in all different shapes and colors and sizes. And these are some examples of amorphous solids. Wow, I can't think of the name of that. Obsidian, there you go, is an amorphous solid, and so is chocolate. This is one of my daughter's favorite things to find on a walk. This is one of my favorite things to take on a walk. So there you go. Supercooled liquids. Glass sags over time. Windows will sometimes get these funny little bows in it. This is a car window, and you can see that the glass has sagged here. And that's just evidence that the glass is a supercooled liquid, not actually a real solid. And you can see that glass, as it breaks, is amorphous. There's no crystalline nature to it. Okay. Crystal shapes are varied. They come in all different sizes and colors and shapes, and there's a ton of them. Look at the tables in your book and see them all. Here's just a couple of quick examples. Cubic, tetragonal, and rhombohedral. Cubic, surprisingly not, looks like cubes. Pretty cool. This is actually a naturally grown crystal. Nobody made this. It grows in the shape of a cube. A tetrahedral has this pointy tip and then, generally speaking, parallel sides until the tip starts to form. And then rhombohedral looks like cubal, but slanted, hence the name rhombus instead of cube. Okay, lots of crystal shapes. Look in your book at them. There are such things as polymorphous solids. Solids that can form more than one kind of crystal. So if a solid could be a sheet or a sphere or a tetrahedron, and those examples are all carbon crystals, we call it polymorphous. It comes in more than one crystalline shape depending on the characteristics of the environment when the crystals are grown. And then there's this last idea, lattice energy. Lattice energy is the energy released when a gaseous particles form crystals. There's more kinetic energy in a gas, right? Sipping all over the place. Less kinetic energy in a solid, sitting there. So when gases become solids, they have to release that kinetic energy. And that energy that's released is called a lattice energy. It's the energy that's released when gases become solids. Now that can go through the liquid state, or it can directly deposit. But in either case, when a gas eventually turns into a solid, we've created a certain amount of, we've released a certain amount of energy, and that's the lattice energy. That's also the same amount of energy you've got to put into the crystal to break it out and become a gas again. Okay, lattice energy. Last thing, and this is such review. You had this, I think you had this for the first time maybe in kindergarten. Melting and freezing. Melting is the point at which the kinetic energy overcomes the intermolecular force. Freezing is the point at which the intermolecular force overcomes the kinetic energy. So the same thing is true for boiling and all that kind of stuff. So Phase changes are just the winning out of one group of forces over another group of forces. Okay, and then we just say that a liquid is a transitional state when the intermolecular forces are strong enough to keep the particles closer than a gas, but not strong enough to lock them up in a solid. Okay, that's a liquid. So you've had this so many times. This is just a cute little reminder that some people are worth melting for, and you know what, you are. So if you have any questions, let me know. Put them in the comments field below. Otherwise, I will see you in class tomorrow, and we will trudge through this together. God bless you. Have a wonderful day.